So today what I want to do, so I want to continue with examples of Hamiltonian G-spaces and reduction. So it doesn't advance that much, but just to get more examples and more feeling of what's going on. And so I have some relatively complicated topics and I have some fun topics. I decided to choose more like a complicated topic to start with, and then there will be fun topics, and maybe in the end, if we have enough time, we come back to a difficult topic. Right, so the first thing I want to discuss is examples of Hamiltonian G-spaces given by so-called coadjoint orbits. So these are the orbits of coadjoint action in G star. So Hamiltonian G spaces. Right, so well, as usual, we choose G, a compact connected Lie group, and we choose a point X in the dual space to the Lie algebra. So then the coadjoint orbit of X, this is simply the orbit of the coadjoint action passing through X. And then we can formulate the following theorem. So there is a unique two-form omega on OX such that the following triple, so we take OX together with its natural G action, right? Since it's an orbit, it has a G action. So the two-form omega that we are trying to define using the theorem, and we'll have the moment map OX to G star, and in fact, this guy already has a natural map to G star because it is sitting inside G star. So, so simply the embedding back to G star. Hamiltonian G space. So in fact, so there is a unique way to make, so this space, to start with, it's not symplectic, no, not at all. It's just an orbit of a group action in G star, but then it turns out that there is a unique way how we can make it into a Hamiltonian G space, and for that we need to figure out what this omega is and to see that it exists, that it is symplectic. So let's try to prove this theorem. So I think on the way I will need a little bit more of Lie theoretic notation, but what to do? So maybe let me start with uniqueness. Right, so I need to show the existence of omega making this triple into a Hamiltonian G space, and then I need to show uniqueness, but uniqueness is an easier. So the uniqueness statement is actually easier. So let me recall one of the defining equations for Hamiltonian G spaces. Right, so we know that contraction of omega, if it exists, with Hamiltonian vector fields, it should be a differential of the functions obtained by pairing the moment map with element of G. So, and this is for all psi in G, right? So this equation, if we are to succeed, this equation has to be verified, right? Now note that if we choose some point, let's say y in the orbit, and if we consider the set of vectors given by restriction of fundamental vector fields, then what do we get, right? So we have an orbit. So the group, by definition, acts transitively on the orbit. Now, if I take all fundamental vector fields and I take all their values, right? This is a subspace of the tangent space to the orbit. But what is this subspace? Right? So you have a group. It sweeps all the orbit, right? So everything. Now you take the corresponding fundamental vector fields, so infinitesimal action of your group, and so you get a subspace. In general, you get a subspace for any G action, a subspace of the tangent space. But what is this subspace now for the orbit? Yeah, so it is you get all the vectors, right? So that's Ty or X. So this means that, so that's because G action or X is transitive. Now, what does it mean, this equation? So here we are actually getting all the vectors. So we obtain a contraction of omega with all the vectors. And then we know the right-hand side. So in fact, this means that omega is determined completely by this equation. Maybe one can make it even more detailed. So we can say that omega psi or x of y, v, where v will be an arbitrary vector here, will be iota v d mu psi. Right? So the right-hand side is completely determined. The left-hand side is omega evaluated on a pair of arbitrary vectors in the tangent space. And so the right-hand side completely determines omega y because it computes it in all the vectors. So there is actually no choice once we postulate the moment map condition. Okay. So that's for uniqueness. So now we need to prove existence. Let me do it in the following way. Let me just give you the formula for omega, and then we check that it's well defined, that it is closed and non-degenerate. So I'm computing omega at the point y, or I don't know, maybe to save notations, we can say we are computing omega in x, because x, of course, was a starting point, but maybe we can denote by x the arbitrary point, as you like. Maybe just to save notations. So omega x. So, and I should compute it on the values of two fundamental vector fields, let's say xi and eta in G. And here there is a very beautiful formula. That's that's why I kind of probably one could have chosen to present it in a different way, but let me do it in this way. So, right, so this will be the Lie bracket of psi and eta paired with x. Right, so these are elements of G. So their Lie bracket is an element of G. So this guy is an element of G star. And you know, there is not that many choices how you can make some number out of these three pieces of data. And so that's a very, very beautiful formula. Of course, we haven't shown yet that it actually works, but let me already tell you what's the name of it. So it goes under the name of Kirillov constant Suryo 2 form, or people often write KKS. So KKS, it stands for this beautiful formula. Right. So from these three pieces of data, two elements of your Lie algebra, and from the element of the dual, you build a kind of nice combination which gives you a number. And this is a value of omega on these two vectors coming from fundamental vector fields. Right. So I'm praising the formula, but to start with, it's even not clear whether it's well defined. Right. So let's discuss several issues: whether it's well defined, whether it's non-degenerate, and whether it is closed. So these are the things to show. Non-degenerate, closed, and, well, above all, yeah, I should have written it on top, well defined. All right. So here, before I will start with the fact that it's well defined, but before doing that, let me introduce a small extra piece of notation. So recall how we defined the coadjoint action. So we were saying that the coadjoint action on X is defined by the following formula. So we take the adjoint action of G minus 1 on Xi and postulate this equation, right? So this is a definition of the coadjoint action. Now I would like, in a similar fashion, introduce a definition of the coadjoint action of the Lie algebra, so the infinitesimal version of it. And here the definition is the infinitesimal version of this definition here. You see actually the same right-hand side as in the KKS formula shows up in the definition. And here just to remind you, so adjoint Xi of X is dio C. So this small adjoint and adjoint star operators, so they're simplified or whatever linearized versions of the capital adjoint. to adjoint operators. So why KKS form is well defined? And why do we ask this question at all? So it's not obvious at first that it's well defined for the following reason. See, we have an action of G on the orbit. This means, I recall there is a map from G to the tangent space at each point, right? So that's how we define the fundamental vector fields. But in principle, this map has a kernel, right? So we may have a stabilizer subgroup. So the action doesn't need to be free. So this means that in principle, there are some xi's and etas for which at the point x, one of these vector fields may vanish. But then the right-hand side, it still gives us some value. Preferably, this value should be 0, right? So let's say we have gx. So this is the kernel of this map, right? And what we need to check is the following. Suppose I consider psi prime equal to psi plus alpha and eta prime equal to eta plus beta, where alpha and beta are elements in the stabilizer, right? So suppose I consider such a situation. Then we need to check that omega x of psi prime eta prime to be equal to omega x of psi eta. Or in other words, so x psi prime eta prime equal to x psi eta. So the stabilizers don't, so if you add something in the stabilizer, then it doesn't have consequences. Let's see, what is a stabilizer? Well, we're speaking of the coadjoint action and the infinitesimal of the coadjoint action, which corresponds to the map from G to the tangent space of the orbit, is this small coadjoint action, which I've just defined. So that's why actually it's easy to write down what this gx is. So these are elements psi, or let's say alpha, in G, such that their coadjoint action and x vanishes, right? So that's the things which don't move the points by the coadjoint action infinitesimally. So now we would need to write this bracket as psi plus alpha, eta plus beta, and show that all the terms, with the exception of the term which is a bracket of psi eta, vanish. Okay, there will be many terms, but let me give you one term as an example. So for instance, there will be this term, right? So x bracket alpha with eta, and we want this term to vanish, right? So what is this term? If we use this formula here, it is minus adjoint alpha star x eta. But adjoint alpha star x, this must be 0, right? Because alpha was in the stabilized Alekseev algebra, and the stabilized Alekseev algebra has this property. So this is actually 0, and this is 0. And of course, there will be this similar argument for beta psi and alpha beta. So all these extra terms vanish. So the form is well defined. Now, what about non-degeneracy? It's non-degenerate. All right, so let's evaluate the kernel of this form. So suppose psi in G is such that x psi eta is 0 for all eta, right? So what does it mean? Let me rewrite it as minus adjoint psi star x eta. So this guy is an element in G star, and is pairing with all the elements of G is 0, right? So it's a linear form on G which vanishes on all elements. So this means that adjoint psi star x is 0. But if this is the case, look at the formula on the other blackboard. This means that psi is in Gx. But if psi is in Gx, this means that the corresponding fundamental vector field actually vanishes at the point x. So we started with the assumption that this psi was defined in a vector in the kernel, and we see that this vector in the kernel is 0. Right? Perhaps just one small remark. So we have this skew symmetric form on G on the Lie algebra, right? And it has a kernel. But when we think of it as a 2 form on the orbit, it has no kernel, right? So here there is a difference. We use the right-hand side, the formula, the least theoretic formula, to define a geometric formula. So this describes here a 2 form on a manifold. So this describes for you some kind of gadget in Lie theory. So the gadget in Lie theory, it has a kernel. We now evaluated that kernel. The kernel turns out to be Gx. But when you go from the Lie theoretic interpretation to the geometric interpretation, in geometry, this Gx, it gives you vectors which are equal to 0, right? So it no longer counts, and the 2 form on a manifold has no kernel, right? Is it? So are you sleepy, or is it too difficult, or is it too easy? Okay, but so the last point is omega x is closed, and here I need your help. I'm always getting all those signs wrong, so you can kind of tell me how to do it. So I just want to compute it. I just want to take d omega x, so the Durham differential, and I want to evaluate it on a triple of fundamental vector fields. So zeta. Right, so I just want to compute it. Now, how should we compute it? So I think there is a Durand formula, right, for this computation. Could you remind me how it works? It's a kind of complicated formula.
It's the derivative of all those things acting on.
Yeah, let's try. But you see the crucial. Yeah. So let's try. So it's going to be something like this, right? So we should take a lead derivative of psi omega x of eta zeta plus cyclic permutations, right?
Yeah.
Plus cyclic. Now that's a crucial. This is an important point. Either plus or minus, right? Minus. Whatever, plus or minus, but maybe you're right. Omega x. And here, what I should take Lie brackets, right? So I take a bracket of omega x with eta x, and here zeta x, and again, whatever, plus minus cyclic. So nobody in the audience is sure of this?
I'm pretty sure it's
Okay, I take your word. I have no idea. Right. Okay. So let's try to compute it. So we have L psi or x, and here we use the magic formula, right, plus cyclic, and we say minus, and here we have to put in psi eta right. So there will be so we're getting two terms, or 6 terms to be more precise. We have cyclic permutations, and one of them has still some geometry in it. So it's a Lie derivative of something. Here I think I'm cheating when I write it. We come to the discussion in a second. Now, and this is just correct. So this is just correct, and then minus cyclic. Now this one is easy to deal with, right? So what happens when we take this guy and add all the cyclic permutations? Yeah, we get 0 because this is Jacobi identity, right? So this is 0 by Jacobi. Now here, let's see what this derivative is actually differentiating. So this eta and zeta, these are simply constants, right? So this guy, we're not going to differentiate. Here I'm cheating. Actually, I say it is x, but this is just the point where we're sitting, right? If we differentiate, in principle, this point is going to move. So maybe it's more honest to write here mu. Right? So mu, just a map of our orbit into G star. And then we evaluate it at mu equal to x. But you know, if you differentiate, then usually it's better to first differentiate and then evaluate. Otherwise, it may not work. So now, but this differentiation is easy again. So we say how the fundamental vector field moves your point. But that we just discussed. So this is actually equal to, maybe I write in a different color. So this is equal to, and we said it should be adjoint star psi now of x, and here eta zeta plus cyclic. And here we can use again, recycle again the same formula. It is minus x zeta eta psi zeta eta minus cyclic. Now, well, In fact, this is just the same story, just put a little bit differently. So this is again a double bracket and sum of cyclic permutations, which means it's again 0 by Jacobi identity. So you know why I had a hesitation about the sign. I think you're right. It's a minus sign because you know, if it were a plus sign, then the two contributions probably would have just cancelled without any Jacobi identity. And this is probably not healthy. So this cannot be true. So this cannot be verified without using the Jacobi identity. Right. So that's the end of the proof. That was the kind of long proof with complicated, least theoretic content. But now let's look at an example. So coadjoint orbits provide lots of examples. And slightly more complicated examples you will look at in the problem set later today, but let's take the simplest example. So we take G to be UN, and then we know that G star can be identified with Hermitian matrices, right? So so these are complex Hermitian matrices. Let me call them X. And we know that the coadjoint orbits, here they are just of this form. Instead of this abstract coadjoint action, we are using a matrix conjugation. So we conjugate our Hermitian matrix by unitary matrices. So now, of course, we can just look what those coadjoint orbits can be. For that, we can choose different options for X. So let's choose the simplest possible option for X. So just a Hermitian matrix which has 1 at the top left corner and 0 everywhere else. Why not? Right. So we want to understand what's the coadjoint orbit, or kind of to learn something about the coadjoint orbit of this point. Let me do the following. So I take X like that, and I claim that this coadjoint orbit is isomorphic to the space of lines or dimension 1 complex subspaces in Cn. So dimension L of L is 1. So why is that? So I can do the following. Right. So let me take X, or let me take an element here. Yeah, I should still probably call it Y, right? Not necessarily this X. So I take any element from the orbit. You see, this is so note that elements. Yeah, maybe first let me say remark. So if we have Y in OX, it's an orthogonal projection. So why is that? We know that it's Hermitian, And we also know that y squared is equal to gx squared g minus 1 is equal to gx g minus 1 is equal to y, right? Its square is equal to itself. That's because x squared is equal to x, right? So all its conjugates, they also have this property. And it's Hermitian or whatever, self-adjoint, whatever language you want to use for that. And this means that it's actually an orthogonal projection on a subspace. Since the dimension of the subspace here is clearly equal to 1, so all its conjugates, they will project us on subspaces of dimension 1. So here y will be mapped to the image of y. So this will be a subspace of dimension 1 because clearly x is of rank 1, y will be of rank 1. And in the other direction, a subspace L will be mapped to the orthogonal projection on L, right? So this is just a one-to-one correspondence between subspaces and elements of this type. Should I make it more detailed, or it's just a linear kind of linear algebra statement? So maybe another remark. So this is more or less by definition the projective space CPN minus 1, right? Maybe one more remark. So remember last time when we were looking at the polygon spaces, we introduced the notion of scaling. At some point we decided we would rescale the symplectic structure. So in fact the same game, I don't know, is there some chalk? So the same game can be played here. So you can, oh no, that's probably not visible. So you can multiply, instead of 1, you can put here some, for instance, some real number, some positive real number, let's say, or in fact, let's say even like non-zero real number. And what will happen, so this will be a different coadjoint orbit. But this description will be still correct. The only thing here, we would have to multiply this orthogonal projection by R in the map from L to the coadjoint orbit. So I think this map is still valid. You just take your element and you consider it as an operator acting on Cn, and you take its image. So that still holds true. What will change a little bit is the symplectic form. So the symplectic form corresponding to Rx will be R times the symplectic form corresponding to X. And this is because, recall, omega x of psi eta is equal to X bracket psi eta, right? So that's the KKS formula. So now if you want to multiply this element by R, we know how it depends on X. It depends linearly, right? So here there will be this R standing. Right. Okay, so that's maybe like the first tour of the quadrant orbits. Perhaps we're going to return to this topic from time to time. And this is an important source of examples. So this is one of the big sources of examples of Hamiltonian G spaces. Maybe, even though we still have 1 or 2 minutes, let's stop and make a break. And then after the break, we'll look at some other set of examples, in particular examples of reduction. And I think they will be easier. These will be like more fun examples. So this was a little bit like tough examples. And after the break, will be fun examples. So, should we restart? Right, so during this hour, I want to kind of, as I said, perhaps show you some easier or more fun examples. So there will be maybe more or less one example that we're going to look at from different viewpoints. And there will be 2 interesting and relatively simple concepts which allow us to kind of deal with those examples. So let's look at the following example of symplectic reduction. So M will be R to N, and I would like to think of it as a copy of Cn. And I'll look at the standard symplectic form. I'm not sure how did we handle those i's. Was it I over 2 or 1 over 2i? And here 1 to n dzi wedge dzi bar. And let me consider the following S1 action on M. It's convenient to write it in complex coordinates. So simply I'll map all coordinates zi to exponential I theta zi. If I'm not mistaken, I think it was last week that you had an exercise and you actually computed moment maps for like much more complicated actions. So let me just write down the moment map. I'm not sure about the sign, but so this is a Hamiltonian action. And if I'm not mistaken, the moment map, which is just now a map to R, I think that's it must be this, hopefully. Is it correct? Might be, right? So now, let's say if I choose some x in R, so then mu minus 1 of x so these are points in Cn such that sum from 1 to n zi squares is equal to minus 2x. And let's say that's for x negative. If I think if x is positive, then it is just an empty set. And if x is equal to 0, then that's just the origin. Just the origin in Cn. So the interesting level sets will be the level sets for x negative. And In particular, let's think of the action of S1 on those level sets. So if x is negative, so that's our level set, and it's clear that the action is free, right? So there is no stabilizers, because at least one of these zi's has to be non-zero. Once one of those zi's is non-zero, then the action is simply free, because that's a free action for zi non-zero. So here it's always a free action. Right. So let's choose x to be -1/2 to simplify things. Then what about the corresponding reduced space? So the reduced space is mu -1 of x divided by S1. And so these are antiples of points in Cn. Now, with the condition that the sum of squares is equal to 1, and divided by the S1 action. So what is it geometrically, this set? One idea how you can understand it is as follows, right? What is this guy? So the level set. So the level set, if you think about it as a subset of R2n, it's a sphere, right? It's a unit sphere. So this is a sphere of dimension S2n minus 1, and here there is this S1 action, so this is a quotient of the sphere by the S1 action. Or what about a complex picture? So here what we have, we fix the sum of squares to be equal to 1. But let's forget about it. Let's, on the one hand, remove this condition and just say that so we are not allowed to have the origin. So let's say this element in Cn is non-zero. And on the other hand, in addition to rotations, allow rescalings, right? So this is more or less equivalent. By rescaling, you can always bring a point here. And then what remains is rotations. So this is actually the same as Cn without origin, divided by the rescaling action by C star. And this is what? Of course, this is our friend Cpn minus 1. So this is a slightly more economic way of obtaining Cpn minus 1 as a symplectic space in comparison to what we had in the previous hour. Even though, remember, there we obtained Cpn minus 1 as a Hamiltonian UN space, right? And I think that's one of the exercises for in the next problem set, to use rather this method and understand the Hamiltonian UN structure of Cpn minus 1. Instead of thinking of coadjoint orbits, thinking in this language, thinking of Cpn minus 1 as a reduction of a vector space. Right. So let's have this. In fact, we're going to return, so more or less during this hour, we'll be always discussing this example, but from different viewpoints. And we need some pieces of machinery. Let me introduce the first piece of machinery, which is maybe it's slightly, yeah, in some way it is easier. So I suggest maybe we don't make it very detailed. Let me formulate it as a remark. And this is called sometimes reduction in stages. Suppose that we have the following setup. We have a product of two groups, G and H, and it acts on our manifold M. So M is symplectic, and the action is Hamiltonian. So you have a moment map, which is just a sum of moment map for G and a moment map for H, and it maps M to G star plus H star. So you just have two commuting actions and two moment maps. We can put them together if we want. So this is G cross H Hamiltonian space. Now, suppose that we've chosen a point X in G star and a point Y in H star. And let's assume that the stabilizer action of mu minus 1 of X is free. And let's assume that Gx times Hy action, so this will be mu 1, mu minus 1 of xy is free. So then the following is true. So the H action descends to the reduced space. Right? A priori H acts on M, but it restricts to the level set, and it descends to an H action on the quotient space. The map mu2, which is a priori a map from M to H star, it restricts to the level set and it descends to Mx, and H Mx, its natural 2 form, and this map, let me again denote it by mu2. It's a kind of slight abuse of notation, but is a Hamiltonian H space. And then you can do the following thing. In this Hamiltonian H space, you can consider now the reduced space for H, which would be mu2 minus 1 of y inside Mx divided by Hy. And this will be literally equal to Mxy, which is mu minus 1 of xy divided gx times hy. And this is as symplectic manifold. So why is it called reduction in stages? That's because it says, suppose you're in this very favorable situation, you have commuting actions, and you have moment maps, and all the actions that you want are free. Then you can first reduce under the action of G and obtain some symplectic manifold, which would now carry only an H action. Then you can reduce under the H action and obtain the reduced space. Or what you can do, you can say, okay, I have a group I choose a point in the dual of the Lie algebra, and this point is xy, and I just directly reduce under the action of the big group. Again, I obtain a symplectic space, and these symplectic spaces, you can say they're isomorphic, but I think they're just canonically the same. Right. So that's why it's in stages. You can first reduce a little bit and then reduce more, or you can reduce kind of under the big group immediately. Perhaps instead of giving you a detailed proof, let me only show you some key parts of it, or maybe like beautiful parts of it, well, not so beautiful parts of it. So let me draw the following diagram. Right, so we have M, and inside M is sitting the level set of xy, and you can quotient it by the gx action. Of course, gx acts there. And you can further quotient it by the hy action. Right? So this is the reduction under the big group. You take the fiber of the big moment map, you divide it by the action of the stabilizer inside the big group, and here I'm just artificially introducing some intermediate stage. We'll now see why I'm interested in it. On the other hand, we have here inside mu minus 1 of x sitting, and here is mx. This is mu minus 1 of x over gx, right? So this is just the reduction under the first group. So here inside, there is mu2 minus 1 of y. So here I'm trying to start the reduction under the second group. And now notice that these two guys are just the same. You know, see, kind of that took me some training, how one draws the diagram that they get close to each other, so as one can write inequality. So this is a kind of exercise in geometry of planar diagrams. Right, but you see why this is the case. So we have a fiber of xy divided by gx. And here, what is this guy? So that's a fiber of under mu1 of x and a fiber under mu2 of y. That is the mu fiber of xy divided by gx. So this is just literally the same thing. And here I should continue to mu x y equal to mu2 minus 1 of y divided by hy. So the passage from this floor to that floor is divided by hy. So since we already got something which is the same at this floor, it will be the same here. Right. So that's why the spaces are literally the same. And maybe maybe one more calculation. In principle, one should show that this mu2 is actually a moment map for the h action on this reduced space, right? So in principle, one should show it. So we know that for psi h, if we take iota psi m omega, we obtain d mu2 psi, right? So just a moment map condition upstairs. Now let's call this map Ix, right? We were calling it Ix, this embedding of the level set back into the manifold. And let's apply this pullback under this map to this whole thing. Well, so here what we're going to get, so I x star yod xi m omega. But you know, since H acts on the level set, so you can do the following. You can say this is iota psi of the level set Ix star omega. And here it is Ix star d mu 2 psi. Right. Now, remember what the reduction formula says, right? We had this kind of main equation for the symplectic reduction. So the pullback of the two form to the level set coincides with the pullback under projection of the symplectic form of the reduced space, right? So here we have omega, here we have omega x, and if we pull them back here to the level set, they should be the same, right? So this was the main reduction equation. So this is actually equal to iota xi mu minus 1 of x pi star x omega. But now we know that the action even descends to the quotient. So this means that we can rewrite it again, and pi x star iota xi mx omega x. Right? Now what about this guy? So we also said that mu2 restricts here and descends to mx. And we call this guy mu2 again. This is a little bit like kind of and this means the following. Of course, here it becomes a little bit ambiguous, this notation. Maybe we should call it mu2 tilde. So mu2 descends to mx and defines mu2 tilde so then this would be this mu2 tilde. So now what? Now we got that this is equal to that. So pi star of what we want is equal to pi star of what we want. But pi star is injective because pi is a projection. So this means that actually what we want is equal to what we want. It's not too abbreviated. Right. So injective, and this means certainly here there are still missing steps, but I suggest maybe those who want fill them in. Otherwise, you see, it's a relatively straightforward thing. So there is maybe the machinery, which is a little bit like kind of filling blackboards, but so maybe instead of like explaining fine print details of the proof, I want to give you two interesting examples of how it works. Well, and the example will actually be the same as the one that we started with. So we're looking at M equal to R to N, isomorphic to Cn. And the 2 form is the standard one. And now what we do, we consider the action of the n torus. So n copies of S1, and this action will be simply a component-wise action. Now, the only problem is kind of this time, maybe I want my moment maps to be positive. So this would mean I would have to change the sign, right? But it's a purely aesthetical detail. Maybe kind of. Right, so the moment map will now have n components. And those components are 1/2 Z1 square and so on, 1/2 Zn square. Now I promised some reduction in stages, so I should tell you what are the two groups that I'm going to look at. So let me choose G isomorphic to S1. To be just the diagonal subgroup inside Tn. So I take all the angles to be the same. Right? It's clearly a circle subgroup of the torus. In fact, we already seen that subgroup, right? That was the subgroup that we were talking about before. And let me choose H to be isomorphic to Tn minus 1. And this will be theta 1, theta n minus 1, 0 inside Tn. So just the last angle is 0, and the first n minus 1 angles are whatever they want to be. So now what can we say? So the previous considerations tell us that if we take mx, for here x will be positive. So x is a positive real, right? So I take the symplectic reduction of my space under the action of the first group at some positive level. So then what happens? So then H acts on mx. So there is a form of the reduced space, and there is this moment map mu2 tilde mx to h star is a Hamiltonian H space. So then there was a statement about the further symplectic reduction, but for a moment, let's just forget it. I actually don't care at the moment. So here is the statement. So I'm getting a new Hamiltonian space for the Tn-1 action, right? So let's write it in more detail. So we have Tn-1, which is acting on the reduced space. So the reduced space, we already know what it is, right? So this is Cpn-1, right? So this is Cpn-1 with points given by the equivalence classes of antiples, Z1 through Zn-1, and the action is just given so the action is given by this formula, right? So Zi maps to exponential minus I theta I Zi for I1 to n-1. In fact, our presentation is even more detailed. So we have them as antiples Z1, Zn with sum 1 to n Zi squared equal to 2x and modulo the diagonal S1 action. So there is some 2 form omega x, and there is mu2 tilde mapping Z1 Zn to 1/2 Z1 squared 1/2 Z n-1 squared. So this is a rather concrete presentation. Maybe an interesting side question that will become important very soon in our course. Let's ask, what's the image of this moment map, right? So we have a map mapping our space to H star, so which is R to the power n-1. And let's ask what's the image of this map. For instance, let's take a simple example, say n equal to 3. In this case, so the image will be in R2. And let's just try to draw this image. Right? So we have, say, 2 axes and A1 and A2, the 2 components of the moment map. And so we want to compute the image of this map. So Z1, Z2, Z3. So sum Zi squares is equal to 2x. Mod S1, but actually mod S1 I don't think it's going to be now important. And it is mapped to a 2-vector 1/2 Z1 squared, 1/2 Z2 squared. So this is our A1, this is our A2. It's already clear that the image is completely in this positive quadrant because they are positive. So what's the restriction on these 2 guys? Well, we see that A1 plus A2 is equal to x minus 1/2 Z3 squared, right? So in other words, A1 plus A2 is small or equal to X. Right, so what we got in the end is the following triangle. And that's the image of our moment map. It's easy to check that for high n, you would always get simplices inscribed in this positive quadrant. So you will have more x's. You will have a hyperplane corresponding to the sum of your coordinates equal to x. And between this hyperplane and the planes, the hyperplanes defined in your coordinate system, you would always have such a simplex. So this would be the images of the moment map for this natural Tn-1 action. And this is actually like, we'll have many more of such pictures later in the course, but this is a first like interesting picture, an interesting polytope, in this case, a triangle, which is associated to a Hamiltonian T-space. Let me finish with one more remark or one more construction. It's an example of reduction in stages, or rather of a reduction. Let me instead do the following. Maybe the construction I introduce next time. And now we do reduction in stage. We proceed with reduction in stages a little bit further in the same example. Right. Okay. So right. So let's still continue the discussion a little bit with this n equal to 3. So I constructed for you this CP2 together with a T2 action and together with the moment map mu tilde to H star, which is here equal to R2. And that's the image of this moment map. Now see here, T2 is equal to S1 cross S1. And we can now try to play the same game again, right? So let's try to do it. We need to choose a copy of S1. Let me simply choose the first copy of S1 as G, and the second copy of S1 as H. So this will be G, and this will be H. And I would like to do symplectic reduction under the S1 action to obtain an S1 Hamiltonian G space. Right? So let's see what's the image of the first component of the moment map. So the image of this first component, which we called A1, that we can read from the picture, that just the segment 0x. Now, perhaps I leave you as an exercise that the S1 action on A1 minus 1 of y is free for y between 0 and x. So this means that I can consider my, which will be A1 minus 1 of y divided by S1. So what will it be? So let's think. So we have, as before, triples of complex numbers. And now we have a condition, sum of the I squares is equal to 2x. And in addition, we are saying that A1 of this antipole, which means 1/2 Z1 squared, is equal to is equal to y. And we divide it now by the action. Z1 goes I minus I theta 1 minus I theta Z1. Z2 goes to E minus I theta Z2. Z3 goes to minus I theta Z3. Right, so there was the reduction that we did in the beginning under the diagonal action, and now in addition we take a quotient by the action of this theta 1. So notice that now the absolute value of Z1 is fixed, and we explicitly divide by its phase. So Z1 we can basically forget, right? So this is the same as now pairs Z2, Z3. Now Z2 square plus Z3 square will be what? Will be 2x minus y, right? So because we take away Z1, and we now divide it just by this diagonal action. But that we already know what it is, right? We already had such an example. What is this guy? What it is as a manifold? Yeah, of course, it is just CP1, right? So this is isomorphic to CP1. Just strangely, we call coordinates instead of Z1, Z2 or Z0, Z1, we call them Z2, Z3, but okay, why not? It's going to be automatically an S1 Hamiltonian G space, right? What is its moment map? Sorry for kind of, it becomes not very plain now, this writing on the blackboard. So what is the moment map? We had a T2 action, and this was actually the moment map for the T2 action. Right? Now we take a reduction under the first component, and the second component remains. So logically, this will be the moment map, right? So the moment map maps it to 1/2 Z2 square in R, right? And the S1 action will be the action rotating Z2. So the S1 action sends Z2 to minus I theta to Z2, Z3 to Z3. So that's the S1 action. So that's this point Y on the A1 axis that we chose. What do you think? Can we read the image of the moment map from this diagram? So what's the image of the moment map of this CP1? So we fixed Y, right, on the A1 axis. Now, what is the moment map? The moment map is 1/2 Z2 squared, but that's what we called A2. So if you simply take this line and you look at this segment, that's exactly the image on the second axis of the moment map of this reduced space. In fact, you can check that the reduced space is a quotient by S1 of the pre-image of this segment. So you take the pre-image of this segment, and then you quotient it by the action of the first circle, and that's our reduced space. So you see the kind of this example already indicates that first of all the images of the moment map they probably simplify your life because they look nice. For instance, here it's a triangle, and also you can think about reduction by more or less looking at the image as well. It tells you something about the reduction. For instance, here we could just, for instance, decide what's the size of the image by looking at the picture, right? Instead of making a computation. All right. So let's stop here. And so next time I will continue this story and show you something which is called symplectic cutting, which is a very, very beautiful application of these ideas. Hopefully my writing on the blackboard will improve by the next time. And let me recall you, next week there will be those students, bachelor students. So I'll try maybe like to make my presentation a little bit easier. We'll see whether it works. Usually one kind of always wants to make it easy, but in the end the results are mixed. But at least let's try it. Well, that's it for today. Thank you.